When you think of the moon, you probably think of its surface. Hostile, barren, and covered in impact craters. The reason the moon's surface is so barren is because the moon lacks two crucial defences. It has no atmosphere, so there's no atmospheric friction to burn up asteroids, and its magnetosphere is so weak that it offers little to no protection against the solar wind. Luckily for us, the Earth does have a magnetosphere, which is a vast magnetic field created by thermal currents in the Earth's outer core of liquid metal. This bigger than planet-sized field of magnetic force, which you can legitimately call a force field, deflects most of the solar wind, which is plasma that the sun kicks out of its outermost layer, the corona. But even more powerful than the solar wind are CMEs, or coronal mass ejections. A CME creates a huge cloud of plasma with magnetic fields embedded into it. Faster moving and more explosive CMEs are more common near the peaks of the sun's 11-year cycle, called the solar maximum, where solar activity peaks, and the most recent peak was in May 2024, just over a year ago, so we're quite close to a peak. Prepare to be really glad that we have the magnetosphere, because the sun just fired a massive CME right at us. Take a look at this. It's from the Space Weather Enthusiast dashboard, and it's really useful for checking out where you might be able to see the aurora, and this bit is the prediction of the recent CME. That little green dot, that's us. It's not a big one, so it's not a cause for concern. There will probably be some interference to high frequency radio, which is used by planes, shipping and GPS, but important things like that have fallbacks because small CMEs happen a lot, and at low levels of interference, GPS can tolerate that. This CME is just kind of funny because it blasts the Earth right in the face. I guess it's kind of like if it rained over just your house. But you know what wouldn't be a fun time? The Carrington event. The Carrington event was the most powerful geomagnetic storm ever. It happened in 1859 and was likely caused by a CME. This is a model of Earth's magnetosphere during a coronal mass ejection in 2006. The lines represent the path of charged particles as they pass by, and the colour represents the density of the plasma. You can see that the shape of Earth's magnetosphere changes quite a lot when a CME happens. Close to the surface of the Earth is where the magnetosphere is strongest, so there's a lot less change. Now, let's see a simulation of the Carrington event. You can see the Earth gets absolutely blasted. We're like a tree in a tsunami. It's quite unsettling to watch. But, spoiler alert, the world didn't end. So what did happen? One of the effects of a CME hitting Earth are auroras. They're those cool, colourful swirls that you see in the sky nearer the poles. Those are caused by fast-moving solar wind, or plasma, from a coronal mass ejection colliding with charged particles in the plasma in Earth's magnetosphere. From those collisions, some of that energy is shed as light. They're striking because they're bright compared to the dark sky, but during the Carrington event they were so bright that gold miners in the Rocky Mountains thought it was dawn and started to make breakfast at 1 in the morning. Two telegraph operators were able to turn off their batteries and still send messages to each other because the rapid changes in the Earth's magnetic field was inducing enough current to power the system. And that brings us to the true chaos that another Carrington event would cause if it were to happen today. For some context, this is a trip down Market Street. Shot in 1909, it shows a very different way of life, with trams, cars and horse and cart shoulder to shoulder in the street. And this is 50 years after the Carrington event. In 1859 there wasn't that much disruption because back then there wasn't that much dependence on what we would call modern technology. But there is now. The modern world is soaked in technology, and most of us depend on it, directly or indirectly, whether we like it or not. In most cases, it makes our lives better, as long as it doesn't suddenly stop working. So what would the impact of a Carrington event be if it was to happen today? It's hard to predict, but there have been studies into this. The power grid uses transformers, and a geomagnetic storm could induce more current into them than they can handle, exposing any part of the power grid that's not robust enough to handle that, especially if they are old and not maintained, which does happen. Satellites in low orbits could have a bad time too, because during a geomagnetic storm, the sun's ultraviolet light output increases, which heats up the planet's upper atmosphere, causing it to expand, and that increases drag on satellites in low Earth orbit. This happened in 1979 when higher than predicted solar activity caused the space station Skylab to re-enter the atmosphere earlier than expected, because the atmosphere heated up, expanded, and slowed the station's orbit down, causing it to crash into Western Australia. You can see pieces of it in museums. That probably won't happen to GPS satellites, but they can be affected in other ways. Let me explain. Starting at sea level, the Kármán line is 100 kilometers in altitude, and it's kind of an arbitrary line where space starts. Then, at 160 kilometers altitude, we have the start of low Earth orbit. 2,000 kilometers in altitude is where medium Earth orbit starts, the band that GPS satellites hang out in. The GPS constellation orbits at about 20,000 kilometers in altitude. You can see that it's pretty far away from the Earth's atmosphere, so it's not really at risk of atmospheric drag pulling it back down. However, GPS signals have to pass through the ionosphere, which bends the path of the signals. GPS accounts for this, but if the ionosphere is being churned up by the arrival of charged particles and magnetic fields from a coronal mass ejection, those signals will take a different path through the ionosphere, which makes GPS less accurate because the time difference between signals from different GPS satellites is used to work out where the receiver is. A lot of planes would be grounded too because you need to communicate where you are and where you're going, and everybody has to be on the same page if you're going to fly 70 tons of jetliner around. All of these things would absolutely affect our daily lives, and it's impossible to know how a Carrington event scale solar storm would play out in the modern world, but I think it's safe to say it would be chaos, but probably not the end of the world. Power grids black out, but they generally get back online. GPS can fail, but we still have paper maps, and flights get cancelled all the time. If we lost a big chunk of power for quite a while, and by extension the technology it powers, we'd survive, most of us. But please don't let this video fill you with existential dread or worry. This isn't like climate change where things are just getting slowly worse, and it's very likely that a powerful geomagnetic solar storm is not going to happen in your lifetime or mine. And we do have forecasting technology now, so we'd at least have warning. So try not to panic about it too much. I'm not. Thanks very much for watching. Please do subscribe if you like the video, and leave a comment if you'd like to see more videos like this. I'll see you in the next one. Bye!